All right. Hey, let's try number 55. Little surface tension one here. It says the pressure inside an alveoli with a radius of 2 times 10 to the 4 meters in radius is 1.4 times 10 to the 3 Pascal. Due to its fluid-lined walls, assume that the alveoli act like little spherical bubbles. I have a hard time pronouncing that word. What is the surface tension? All right, so let me take a moment just to kind of remind you that, if you made a bubble, and if you go back to the video lecture, I kind of used a soap bubble here as my example. But I made the soap bubble in class, and so what's going to happen is you've got this spherical bubble, the shell, and the tension wants to pull in on it and kind of wants to group it all together. Of course, there's air in here, and so the pressure builds up. And so there's a balance effect between, I'll call the top hemisphere getting pulled into the south hemisphere by the surface tension, so the whole thing wants to collapse, versus the pressure from the air molecules inside pushing backwards, okay? So if we remember that pressure is force over area, then we can say force is the air pressure times the area. And so you've got this hemisphere being pushed upward by the air pressure. And so that's really the question right there, the P. What is the pressure inside this balloon? Now, the areas can be a little confusing because we don't really want the area of the hemisphere because the force, maybe I'll use a different color, would be pushing outward, but it would have these X components, not just the Y component. And so if you really wanted to know the total upward force, you've got to add up a bunch of little vectors where the angle changes. And we can simplify that by saying, well, instead of looking at a component of the force, let's look at a component of the area. So if you think about kind of the surface pointing up like this, and you only want the vertical piece, that would be same as the shadow pushing down, and that would be the area of a circle. And so without actually doing the calculation, I'm going to put pi r squared for the area of a circle, that representing the vertical component of the area, which, like I said, would really be the vertical component of the force and then times the whole area, but it's kind of easier. And we saw this actually really well in chapter 9 where we did the torque. We took a wrench, we put it on a bolt, and if we applied a force on this bolt sort of in this direction, since the wrench has to turn along this arc, we call this angle here theta, we would only want the component that would go in the direction the wrench moves. So we would want F and then sine theta. However, we said if you then multiply it by the area, instead of saying that this is the force you're interested, group these two together, and that would be drawing the line of action, and then you can just do a perpendicular distance, which, as we struggled in chapter 9, that's a little kind of confusing because it's like, wait a minute, there is no distance there, but true. So if you want to stick to the real physics of it, you want the sine theta to go with the force and the r to go along the wrench. However, that is equivalent to a perpendicular distance, and it's just easier to see. And that's what I'm trying to say here. Technically, we really want the force times, some sine of some angle. But instead, we can group it with the area and, well, oops, I said that wrong. I want pressure. I want, pressure times sine theta. But instead I can put it with the area, and then that's easy to see. It would just be kind of a shadow effect that you would get in a plane of the vertical axis. So that's kind of my conceptual way of saying the area we want is kind of the shadow area because of the components. And that's why I'm going to put the area as pi r squared, because the area of a hemisphere would be 2 pi r. And I'm not going to use a 2 here. It's the area of a circle. All right, so it's the air pressure in the area of a circle that's lifting the hemisphere up. And then, of course, what's pulling it down is this surface tension. And there would be both an inner surface and an outer surface kind of holding the liquid together. And so we use the symbol gamma for the surface tension, and that was the surface tension per length. So it's being held together along this equator, and the circumference on an equator is 2 pi r, and that is the force per surface, and I'll multiply by 2 then, because there is a top and a bottom. And then the equation simplifies a little bit by canceling off a pi and an r, and over here you get a 4 gamma, and then a 4 gamma divided by r is the equation we worked out in class for the bubble, if you will. So for this problem, we're asked to find the surface tension. So let me rearrange this equation by saying pressure times the radius divided by 4 would give me the surface tension. And I think they said this pressure where it is 1.4 times 10 to the third pascals. Okay. The radius of this, 2.0 times 10 to the fourth meters. Okay, good. Then divided by 4. And that should give me the surface tension. Notice this Pascal then is a Newton per square meter, so it's going to cancel with one of those, and so we are going to get the appropriate unit for surface tension, which is how much force per length, and that's the meaning of surface tension. I like to say it's the amount of force per length per each surface. So when you have a bubble, you've got an inner surface holding it together and an outer surface, and so that's where that factor of 2 comes into play. But when we did the capillary effect, there was no top and bottom surface. There was just one surface as we went around the capillary tube. So we didn't have that factor of 2. So it's important to remember that surface tension here is in units of newtons per meter, but it really means the amount of force per length per each surface. And that's an added important piece of this. All right, well, so to get an answer here, I'll go 1.4 times 10 to the third times 2.0 times 10 to the fourth, then divided by 4. Oh, my bad. I think there's a little minus there. That would be a huge radius here, wouldn't it? It doesn't even make sense here. All right, let me try that again here. I'll just go edit. Right there, and I need to insert a negative. Okay. 0.07. That sounds like a very reasonable number for surface tension. And I'll do 3 significant figures. Okay, so here's my surface tension. There's A. And then B, what does B says? Try to identify this. Look at the table. And now that we know the surface tension, and every liquid is slightly different, maybe we'll have enough accuracy to kind of pinpoint what kind of fluid it is. So let me reach over here, grab my book, kind of bring it into the screen here, and looking here in chapter 11 under the fluids, table 3, your author listed quite a few fluids. 0.07 is looking a little bit to me like it might be the blood plasma as opposed to the whole blood. And given that it's in the body, I know it's 37 degrees Celsius. Maybe that's a hair high, but maybe it's not purely whole blood. Here I don't know enough life science to really answer this well. You know what? I know the lungs have a lot of moisture on the surface, and they're obviously designed to mix with the oxygen. So my guess is we're probably looking at human blood, although if I look here at water, kind of the same thing. It looks like if we follow this pattern for the water, it might be water at about 37 degrees, which is this. So anyways, it would be hard to tell whether it was pure water or water with some kind of ions and other stuff other than the red blood cells, and looks like that would drop it a little bit lower. Anyways, I'm going to go with maybe water. Yeah, a water at 37 degrees or your blood plasma at 37 degrees. And given that it's in the lung, doesn't really surprise me. Although, yeah, as we talked about earlier, the lungs have those special amazing molecules. What were those called? Surfactants. And those surfactants are just crazy and amazing. So they could be that too. Anyways, I'll call it quits here, and hopefully that was helpful.